there is a difference between the states regarding. So we know that gaseous state it is characterized by energy only. Since there's no interaction between molecules, or almost no, since the only interaction is in the form of collisions between molecules. That's why, if we have to express internal energy, we have to take in mind just the kinetic part of this energy, since all of it is in the form of kinetic energy. Then, so just to see. So then this example, which is to show what? That molecules, gas molecules, are in constant motion with enormous velocity, very big velocity. So, and as an example, nitrogen molecule is taken, which is a substantial constituent. So the mass, you can see very small, 10 power minus 26, you know, point, and then 504 kilograms. So small is the mass of this molecule, and the diameter also 1/10 of meter. So, but it is excessively active. So it has got very big kinetic energy since its velocity is given approximately as 490 meters per second. How to find this quantity? So we're not losing time to focus on very important things. I'm just going to solve this problem, if I can call it a problem, conceptually. Conceptually means in the form of an equation. So that's let me switch on the board here, and let me write in what way to express the internal energy of an ideal gas. It depends on temperature. So thus the internal energy mean 1 is 3/2. There is a constant which is called Boltzmann constant. Its exact value you can see in the red practice book. In the beginning of the book, there is a table dedicated to constants and Kelvin temperature. So thus this internal energy is, as I have just told you, entirely given as kinetic energy. So thus, mean kinetic energy, you know the formula for the kinetic energy, half mv squared. So thus, left-hand sides are same. We can equalize the right-hand sides. So thus, for what purpose? To express the velocity, because this is what we want to know, which is given as a numerical value in the slide. So we've got kT and 1/2 mv squared. So we can cancel those numbers, and then we can write just v squared is K3 kT divided by the mass, and just the velocity is root square of that ratio. 3 kT divided by the mass. So in this formula, K, I told you, so I have by here that book, so, and I can So the page is 9. The Boltzmann constant is in the third position, 1.38 times 10 power minus 23 joule per Kelvin. So this is the value. Temperature, since in the presentation, you can see that at 0 degrees Celsius is given what is the velocity. Because the internal energy, as you have already seen in the formula, is directly proportional to the temperature. But Kelvin temperature, that's why in the equation you will not write 0, but you'll write 273.15 kelvins, which is the corresponding temperature in kelvins to 0 degrees Celsius. And mass also is given in the slide. Just to find the pointer. So it's given here, the mass which we also discussed. So that's all the quantities. And substituting in the formula, and if you calculate this correctly, you must find that number 490. So that's it's a conceptual solution. So we solve that as a formula, which is the most important, solving some physical, biophysical problem. So let me make this bigger. So and proceed with the next part. So velocity is and gaseous molecules are extremely active. They are in constant motion, they collide with each other, and if they are placed, that gas, hydrogen, is placed in a container, it will bombard each molecule, will collide against the wall of the container, and it's given here millions of collisions with the walls each second, millions of collisions, which means that those collisions, they exert what? Pressure on the container walls. So, and really, this pressure of the gas is the reason for the transport phenomena we are going to discuss today. So that's in case of liquid and gaseous state, we've got difference. What is the main difference? That molecules possess both kinetic and potential energy, not just kinetic, as in case of gaseous state, both. But what is the difference between liquids and rigid bodies or solids? So what is the difference? The difference is that in case of solids, molecules are very limited in their motion. They can vibrate only about some equilibrium positions. In case of liquids, molecules behave like sticky spheres. That's why we are talking about short range arrangement of in case of their structure. So let us proceed here. So in this slide, this is the beginning of the explanation of a phenomenon which is termed diffusion. Diffusion here is defined very descriptively. I'm going to suggest you proper definition, really, scientifically. So here it is stated, process by which molecules intermingle as a result of their random motion. Random, with no preferred direction. This is the meaning of random. In all possible directions with no specified direction being taken. So that diffusion is a spontaneous transport of matter from area high toward area of low substance concentration. So that this is the definition of diffusion. Diffusion is a spontaneous process. Students frequently state diffusion does not require energy to occur, which is absolutely wrong. Yes?
Can you repeat?
Pardon?
Diffusion, can you repeat?
To repeat what? Diffusion. I like now repeating it in another way. Spontaneous processes mass or matter transport from area of high toward area of low concentration. In other words, so we've got process which require energy. So we mustn't forget this. Since if there is motion, there's no way some motion to occur if there's no energy being used for that purpose. So, but what is the energy? We have just discussed it. This is the internal energy. The energy of random disordered motion of molecules. This is the source of energy. And in case of diffusion, since for it to occur, there must be area bigger and area less concentration. This means that there must be some concentration gradient. So this word, we already know gradient. It is a change in a quantity with distance. So in case of concentration gradient, we've got change in concentration per unit length. There is an example here of two gases which intermingle as a result, and some more explanations regarding molecules. So let me try to provide a picture, our picture, to explain, and then we'll write the equation of diffusion. So it is called Fick's law, but students sometimes know. If they are asked to write Fick's law, they know. If they are asked to write the law of diffusion, they don't know it, which is very strange, since it's one and the same. Law of diffusion and Fick's law is one and the same. So clear, of course, the thing we've written already, and let us consider a container. So we may have some membrane, we may not have a membrane, but if there is a membrane, the membrane must be completely permeable. So, and we've got you know that after some time they must start working, I hope. Okay, I'm going to now maybe it's okay. So we've got a container and the left side being more concentrated. So thus, for the sake of explanation, we consider non-selective or completely permeable membrane, which does not present any obstacle to the movement, and the molecules are in constant motion. They collide with each other, they collide with the membrane as well. But in the left we've got more molecules, then in the right, that's why it is much more probable. So let us see, 2, 4, 6, 8. So more than almost 3 times more likely is a molecule from right to enter the left, to enter the right compartment, and the same times less probable is the molecule from right to enter the left compartment. So thus I would like to tell you, so this you must understand, that diffusion is the spontaneous process of transfer from left to right, but this does not include motion in the opposite direction. On the contrary, however, more molecules will pass from right to left. That's why we state net motion is from left to right, net motion. So for not considering the absence of motion in opposite direction. So there is, but the number of molecules there is less. That's why the net motion is from left to right. So spontaneous means what? That the process uses its own internal energy. This is the energy of random disordered motion. And as in biophysics, in physiology, or in many other disciplines, we'll state spontaneous processes occur down their concentration gradients. There I mean particle concentration gradients. So spontaneous processes occur. So I'm going to write those important words down all along, which is one and the same, what? Concentration gradient. Down or along concentration gradient. What does it mean? It means from high to low concentration. This is the meaning. Down all along. And we'll study, of course, in biophysics. Today we will mention active transport, which works exactly in opposite direction, and we then use terms not down or downhill, but up or uphill or against concentration gradient. So because the process occurs then in active transport from low to high concentration region, and it requires external energy as ATP hydrolysis. But there's no such a situation, no energy is needed for diffusion to occur, which is completely wrong. So thus now the law of diffusion, which also is called Fick's law. So let me write it. So we'll write it in several ways. So initially, the rate of mass transfer. So this word combination, rate of mass transfer, is given mathematically as delta M per delta T. What does it mean? Mass being transferred per unit time. Since we the meaning of the term rate. Rate means change over time. That's why the rate of mass transfer is proportional. So I'm writing coefficient of proportionality, D, which is called capital D, which is called coefficient of diffusion. Then concentration gradient is directly proportional to the concentration gradient and the cross-sectional area through which the transfer occurs. So this is one way of writing Fick's law, the rate of mass transfer. Sign minus it shows that transfer occurs from high to low, not from low to high. And if we have to represent graphically diffusion, in what way concentration changes over space, so then we've got what? So you see X increases from 0 to left. However, concentration decreases. So this thing is reflected in the equation and exactly showing that process occurs from high to low, not vice versa. So let me rearrange the equation in what way? To write cross-sectional area in the left part of the equation. So let us write it. So thus, mass being transferred per unit time, per unit area. This is called flux. Flux, in this case, since we may have different fluxes, flux, I'm writing here for not flux. In this case, so we can express the equation in a simpler way. Flux of matter. In this case, we've got flux of matter. It is proportional to the concentration gradient. So bigger the concentration gradient, bigger the flux of matter, or the amount of matter being transferred per unit time, per unit cross-sectional area. So thus, this also is called Fick's law. This is Fick's law, and Fick's law is the law of diffusion. So I have repeated this many times for memorizing it. So here I would like to derive the unit for the coefficient of diffusion using the Fick's law. So for that purpose, I'm going to clear some space and let me express the coefficient of diffusion using the equation in red. So we've got delta M divided by delta T divided by delta C divided by area, and in the numerator that small distance delta X. So that sign I may omit here since the aim is to find the unit of measure. That's why we may omit sign. So using square brackets, we denote unit of measure. This we also studied. That's why if you see such a written thing, you must know that the unit of measure for the coefficient of diffusion is, and what to do? To substitute units of all the quantities in the right-hand side of the above equation. So thus, mass is measured in kilograms. Distance is measured in meters. Time is measured in seconds. So we use what? Usually base SI system of measure. Delta C, in this case, we've got mass concentration, which is mass per unit volume. So analogously to density of liquid, we use concentration. So thus we'll write here kilogram per meter cube. And then area is measured in meters squared. So thus, mass in kilograms, distance in meters, time in seconds, kilogram per meter cube for the concentration, and finally meter squared for area. Okay, so let me now simplify. We can cancel kilograms. We can cancel meter squared with third power, and what is left? The unit of measure for the coefficient of diffusion is meter times meter is meter squared per second. So thus, this unit is the same as what unit? Unit for acceleration. So coefficient of diffusion has the same unit as that of acceleration. So thus, let me now switch on the slide. Corresponding one. And see if it's low. So here in yellow, this thing which I discussed regarding the net motion, which is important to understand, and fixed low in its more extent form, expressed in terms of the rate of mass transfer. So also here, which is not well visible because of this rectangle, heating and mechanical stirring can substantially hasten or increase the rate of then osmosis. What is osmosis? Diffusion, kind of diffusion. And you may be asked, so osmosis is also diffusion. Then what is the difference and what are the similarities between diffusion and osmosis? Initially similar. Both occur along concentration grade. Both are spontaneous processes, which means that both they use internal but not external energy. These are similar. What are the differences? So, in case of osmosis, solvent molecules are transferred, and in case of osmosis, there must be semi-permeable membrane. And just two types of molecules. One type of molecule is that of solvent. Another type of molecule is that of solute. So these are the differences and the similarities. So I would like here to provide reasoning for the main formula of osmosis. What is the main formula? Van Hoff's law, which gives us the way quantitative to calculate osmotic pressure. So let me explain this. It's so strange. Students study this phenomenon in many disciplines, but can't explain the osmotic pressure. Can't explain what. So this is the important thing, which is like a apparent contradiction. So we've got solvent molecules which are transferred from less to high concentrated solution. But we don't need active transport then. How to explain this and why? This is possible. So this is the question which you need to know and to understand them. So let me try to explain this using a law which every student knows. It is the ideal gas equation, which is the starting point. Just a moment, since there is an important council, I have to join. Da. So sorry very much, but I need to vote in the election, and I must have to vote for an important decision. That's why I needed to interrupt the lecture. So we were discussing osmosis, and I wanted to show you how to for the formula Van Hoff's for osmosis and osmotic pressure. So let me switch on the board, clear of course everything, and again begin with a container. So in this case, the membrane is semi-permeable, which means that just two types of molecules. We've got solvent molecules. So let, for the sake of better explanation, we've got pure solvent in the left compartment and some solution of specified concentration in the right compartment. So we've got solvent and solute molecules being bigger. So thus, the membrane is semi-permeable, which means that it allows passage of solvent, but not of solute molecules. For example, because of mechanical reasons, the size of the pores is less than the size of the solute molecules. Let us assume this reason. And so what will happen here? We've got, let us focus initially on left. We've got solvent molecules which are in continuous random motion, colliding with each other, colliding with the membrane, but they can cross it. As a result of this collision, they will enter the second compartment. So thus, let me, by P1, denote the pressure which the solvent molecules exert on the membrane from the side of pure solvent. So, let us focus now on the right compartment. We've got here, again, solvent molecules. They are also in constant motion. They also collide with each other. They also collide with the membrane and also will exert pressure, but I'm going to use a smaller arrow to denote that this pressure is less. Why? Because we've got less solvent in the right compartment. The number of solvent molecules per unit volume is less in the right compartment. However, there are solute molecules which also are in continuous ceaseless random motion, colliding with each other and also colliding against the membrane. I'm going to denote it by PS, being pressure produced by solvent molecules, but they cannot cross. Nevertheless, they exert pressure. In fact, the solutions in the container are at rest. They do not as a whole move, which means that we've got equilibrium situation, which means that the pressure exerted from the left must be equal to pressures exerted from the right. So thus, let me write now P1, this is due to the fact that there's no motion. We've got P1, which is P2 plus PS. And let me express the difference between those two pressures. What is this difference? This is the difference between the pressure exerted by solvent molecules from both sides on the membrane. And that difference is called osmotic pressure. Let me use symbol pi. There is pi constant 3.14, but this pi is osmotic pressure. And you can see that this osmotic pressure is equal to the pressure exerted just by the solute molecules on the membrane, which means that if we can calculate or find or measure the pressure just applied by the solute molecules, then we will know what is osmotic pressure, which is defined in this way on microscopic level. So Do you understand now why is this transport passive? Because solvent molecules move from less, or in this case, zero concentrated solution to higher concentrated solution. But this is along its own gradient, because if the solution is less concentrated, this means that there's more solvent there. That's why solvent is moving from area where it is more to area where it is less. That's why completely passive along the gradient, but regarding just solvent, since solute molecules cannot pass. And Van Hoff was very clever to suggest a way to calculate osmotic pressure, since those P1 and P2 are not easily measurable. So, and he established a theory considering the solution fairly high diluted, which means that there is almost no action between solute molecules, which means that the behavior of that solute can be explained by universal gas law. So let me now write the universal gas law regarding the solute. It is nRT. And we would like to express the pressure of solute only so number of moles per unit volume, which is concentration, so that's RTC. So see now how much is it interesting. It's a phenomena in fact related to motion of solvent. However, it is calculated using the formula for the pressure of solute. So how to explain this? So if the concentration, they are related, so the formula tells us exactly osmotic pressure is equal to the pressure which the solute exerts on the walls and on the membrane. What is the difference then? They are equal in magnitude, but they are opposite in direction. Since that pressure exerted by solute molecules is from right to left, but osmotic pressure is what this difference, and it has got the direction of bigger pressure, which is P1. So thus we've got osmotic pressure direction from less concentrated toward higher concentrated solution. If we've got solution here as well, less diluted and more diluted, then we will talk about what? The net osmotic pressure. Since each solution has got its own osmotic pressure, as we are going to discuss this presently when we'll discuss molecular transfer across capillaries. Thus, Van Hoff's formula. So thus Van Hoff's formula finally can be expressed, since this is exactly equal in magnitude to osmotic pressure. We may write the equation. In case of electrolytes, there is some isotonic here coefficient in case of the existence of dissociation processes. So I am not going, since we've got really today many things to discuss, I am not going to discuss things which you are supposed to know. So here, in my picture and in this one, so molecules will enter the second compartment, thus increasing the volume. And increasing until when? This will happen. Until this will rise, this level. So, in fact, differences in levels, this means then what? Differences in hydrostatic pressure, which we already studied in the previous lecture. We must have known. So thus, hydrostatic pressure net one is from right to left. So that osmotic pressure is from left to right. We have just written this. So that osmotic pressure is exactly balanced. Osmotic pressure, then this level will stop changing, and that level is a measure of what? Of the magnitude of osmotic pressure. Is an experimental way for measuring osmotic pressure in devices which are called osmometers, and to cover specific topic in biophysics, how to measure osmotic pressure and compare osmotic pressure of two solutions. So thus, unit of measure, any unit of pressure is applicable to osmotic pressure. Different terms regarding the magnitude are used, but pay attention, they are useful but the relative terms. You cannot say this is hypertonic. Hypertonic in relation to what? So it must be always specified. So not in general. To continue further regarding bodily fluids, plasma is a reference fluid, and it can be substituted by 0.9% sodium chloride solution, which is called isotonic with blood or with plasma. Because it has got one and the same osmotic pressure as that of blood. And so here you can discuss what would happen if a red blood cell is placed in hypertonic in relation to plasma solution or hypertonic. What would happen, you must know if you understand the osmosis. If it is hypotonic, what does it mean? So water will enter the erythrocyte, they will burst. If hypertonic, water will leave the erythrocyte, they will shrink. And the third passive transport, which is also a type of diffusion, it is a kind of diffusion, it is called dialysis. Dialysis, again, what are the differences, similarities between diffusion, osmosis, and so, in case of similarities, always we stated osmosis helps to heal, process spontaneous, occurs down the concentration gradient, uses the internal energy of the system, not external energy. However, the difference main is that not one type of molecule, such as solvent molecule in case of osmosis, but more than one type. Several types of molecules can cross the membrane. So this is the only difference. Not one type as in case of osmosis, but more than one, and they are given example, water, salt, glucose, urine, and other organic molecules all can cross, but big molecules such as proteins, particularly albumin, cannot cross. Fine. This determines another difference, the type of the membrane involved. It is called, in this case, selectively permeable. In contrast to osmosis, semi only in case of two types of molecules. Here we've got several molecules that can cross. That's why the membrane is called selectively permeable. In biophysics, we'll use another term, perm selective. This is also possible, perm selective. So, for the discussion will be about the kidney, since that term dialysis is used frequently in relation to kidney function. So, but you will understand that it's better to say that it is related to artificial kidney, not just to kidney and its normal functioning, since we've got not just dialysis, but glomerular filtration is the main process. So that's nephrons being the main base unit of kidney, million nephrons. They are each nephron consisting of two main parts, glomerulus and the tubule. So we've got in this glomerulus, we've got capillaries, and you see that substances that need to be transported to the tubule must cross two membranes. Really, the driving force here is the positive pressure produced by the heart functioning, which means hydrostatic pressure gradient. And this you must know, if the driving force is hydrostatic pressure gradient, this process is called what? It is called flow, volume flow, described by Poiseuille's law, and another term is filtration. Filtration is a process that occurs in response to hydrostatic pressure gradient and is described using Poiseuille's law. You know, Poiseuille's law says volume flow rate is proportional to what? To the pressure gradient of in particular to hydrostatic pressure gradient. Since we've got two pressures, upstream and downstream, to which must determine the fluid flow through the tube. So that's filtration, not dialysis. So dialysis, which means diffusion of more than one type of molecule, is observed in the tubule part of the nephron, but you may see here. So we've got glucose. Glucose, it will require some transport protein. It won't be simple diffusion, maybe facilitated. We've got sodium, potassium, which means charged particles, ions. They cannot cross the membrane because membranes are hydrophobic. They possess hydrophobic core, which means that some active transport systems are involved. That's why the process is much more complex than just simple diffusion. That's why I told you that the term dialysis is commonly referred to artificial kidney or dialysis machine. So you will have in the next semester in the biophysics practical part of the topic. It is biophysical explanation of hemodialysis, and in that topic you will measure an important parameter, the Hall constant, which determines the duration of such a procedure, and you will understand better the mechanism of this life-saving procedure, since it is applied in case of kidney failure and absolutely necessary to remove waste products from the blood. And large volumes of specific fluid called dialysate are placed in contact with the blood via membrane, and that dialysate is very much controlled regarding content for the concentration of waste products, but also of vital ions and molecules at necessary optimal level. So that's why I'm not going to explain this more, and let us just mention active transport. I have done it already. Transport is the chance against concentration gradient from low to high concentrated region, which requires external energy and energy release during our free energy currency ATP. So, perhaps since now we need to start discussing this, which is molecular transfer into pure and it needs some more time, so just some small break of 10 minutes, and then we'll continue with this molecular.